Welcome to lecture 14b on rank and dimension. So far, we have two main algorithms for finding bases and dimension of special subspaces, the image of a matrix and the kernel of a matrix. In both cases, the dimension is easy to compute if we know the rank of the matrix. We have also done a lot of row reducing. In this lecture, the theme is to use tricks to avoid doing row reduction. The dimension of the kernel of a matrix is the width of the matrix minus the rank of the matrix. If we sum them up, on the left, we get the dimension of the image plus the dimension of the kernel. On the right, we have the rank of A plus the width of A minus the rank of A, which is equal to the width of A. This gives us what is called the rank-nullity theorem. It says that without doing any computation, without knowing the rank of the matrix, we know that the sum of the dimension of the image and the dimension of the kernel of the matrix is the same as the width of the matrix, which is the number of columns. Nullity of a matrix is an old word that means the dimension of the kernel of the matrix, but we will not use it much. In this exercise, I have a matrix A, and I am told that the image of the matrix is a plane in R3. I want to find the dimension of the kernel of A. We will try to avoid doing any row reduction to answer this question. It says that the image of the matrix is a plane, which is a two-dimensional object. This tells us that the dimension of the image of A is 2. The dimension of the image of the matrix could be found by row reducing and counting the number of columns with leading 1. But that is exactly what we do when we are computing the rank of a matrix. So in general, the dimension of the image of a matrix is equal to the rank of the matrix. So because the dimension of the image of this matrix is 2, we can say that the rank of the matrix is 2. We have seen in general that the dimension of the kernel of a matrix is the width of the matrix minus the rank. The width of the matrix is 3 and the rank is 2. So the dimension of the kernel of the matrix is 1. Alternatively, you can use the rank-nullity theorem, which says that the dimension of the kernel plus the dimension of the image is the same as the width. Geometrically, the fact that the kernel of the matrix A is 1 means that the set of vectors sent to the zero vector by the linear transformation of the matrix A is a line through the origin in three-dimensional space because the matrix is 3 by 3. Now we will look at subspaces where the dimension is easy to find. Let's consider several special cases. The zero subspace of Rn is the subspace which contains exactly one vector, the zero vector. Note that this is the only subspace with finitely many elements. If there are more than just one element in a subspace W, there must be infinitely many elements in W. The only zero-dimensional subspace of Rn is the zero subspace. The basis is the empty set. The empty set contains no element. Now let's look at matrices of rank 0. If an REF matrix has no leading 1, it must be the zero matrix. A non-zero matrix cannot be turned into the zero matrix using elementary row operations. So the only matrix of rank 0 is the zero matrix. Conversely, we can talk about the largest possible dimension for a subspace in Rn. Recall that a subspace of Rn has dimension at most n. So a basis for a subspace of Rn has n or fewer vectors. The only n-dimensional subspace of Rn is the entire Rn. For example, if I have a subspace W of R5 and I know it has dimension 5, then W must be the entire R5. Matrices of maximal rank are not unique. For example, if the matrix is square, any invertible matrix has largest possible rank. We can also say a little bit about dimension or rank 1. A subspace is one-dimensional if the subspace consists of multiples of a non-zero vector. Geometrically, this would be a line through the origin in n-dimensional space, potentially very large dimensional space. As for matrices of rank 1, Here is a fact which you might have noticed earlier. A non-zero matrix has rank 1 if and only if all the columns are multiples of each other. Equivalently, a non-zero matrix has rank 1 if and only if all the rows are multiples of each other. This is because rank is preserved under transpose. In this example, the rank of this matrix is 1. We see that all the rows are a multiple of each other. Similarly, you can check that all the columns are a multiple of each other. If we do row reduction, we would get this row echelon form. It's clear from here that the rank of the matrix is 1. In this exercise, we have a 2x2 matrix, so we can easily do row reduce to compute the rank of the matrix, but let's practice applying the methods from this lecture instead of row reducing. Because the matrix is 2x2, the highest possible rank should be 2. The other options are 1 and 0. We see that this matrix is not the zero matrix, so the rank could not be 0. In the previous slide, we saw that a matrix can have rank 1 if the rows are multiples of each other, but we see that this is not a multiple of the second row, so the rank could not be 1. So it must be 2. We saw that the dimension of the image of a matrix is the same as the rank of the matrix. So the answer to part B is also 2. One way to compute the dimension of the kernel of A is to do row reduce to a row echelon form and compute the number of columns with no leading one. This is the same as computing the number of columns of the matrix minus the number of leading ones. The width of A is 2 and the rank is 2, so the dimension of the kernel of A is 0. The only subspace with dimension 0 is the 0 subspace. That means that the kernel of A is the 0 subspace, so it contains only the 0 vector. So the only vector sent to the 0 vector by the linear transformation of the matrix A is the 0 vector. In this exercise, the matrix is 3x3, and we want to do the same things. The highest number for the rank of a 3x3 matrix is 3. So the possible options are 0, 1, 2, and 3. B is not the 0 matrix, so the rank could not be 0. To have rank 1, the matrix has to be so that all columns are multiple of each other. We see that the first and second columns are multiple of each other, so that's a good sign. But the third column is not a multiple of 1, 1, 1, so the rank of B is not 1. There was a fact that we learned a while back. If a matrix has 2 columns that are equal or 2 rows that are equal, that means the determinant of the matrix is 0. Determinant of a matrix being 0 means that the matrix is not invertible. B not being invertible for a square matrix means that the rank is not maximum. So the rank of B is not 3. The only choice left is 2. So the rank of B is equal to 2. The dimension of the image of a matrix is equal to the rank of the matrix, so the dimension is also 2. The dimension of the kernel of B is the width of B minus the rank of B, so I have 3 minus 2 equals 1. Similar to exercise 5, I get a subspace, which is a line through the origin in 3-dimensional space. We can also relate dimension to containment between subspaces. Suppose V and W are subspaces of Rn. If V is contained in W, possibly V is smaller or V is exactly W, then the dimension of V is smaller or equal to the dimension of W. This makes sense if we think of dimension as a measure of how big a subspace is. If V is contained in W and the dimension of V is the same as the dimension of W, then V must be the same thing as W. You cannot have 2 different subspaces, one contained in the other with the same dimension, but not the same thing. Suppose we are in R3 and W is a plane through the origin. Suppose V is a subspace contained in W with dimension 2. This means V is also a plane, and V must be this entire plane. So V is equal to W. Since W has dimension 2, V, which is contained in W, can have dimension 0, 1, or 2 by the first statement. If V has dimension 2, then like we said, V must be the entire plane. If V has dimension 1, then V must be some line in W through the origin. It might look like this or some other line as long as it goes through the origin and it stays in W. If V has dimension 0, then V can only be the 0 subspace because the 0 subspace is the only subspace with dimension 0. Next, we will talk about the connection between the rank of a matrix and products. Suppose I have two matrices so that the product AB is defined. I will show that the image of the product is contained in the image of the first matrix. We want to show that as a set, the image of AB is contained in the image of A. The symbol means contain in or subset of. This is similar to what we have done before. We start by saying let V be in the smaller subset. And then we want to write down what it means for V to be in the image of AB. This means that there is some vector W so that the matrix times W is equal to V. This means that ABW is defined, and note that we have B and W. B is a matrix and W is a vector, so this product is again a vector. This means that V is equal to the matrix A times some vector. This shows that V is in the image of A. Since this argument works for all V in the image of AB, we can say that this set here is contained in this set. The next part will be a short argument using part 1 and theorem 3. We want to show that assuming this condition, the rank of AB is less than or equal to the rank of A. Since the image of AB is contained in the image of A by part 1 of this exercise, theorem 3 tells us that the dimension of this subspace is smaller or equal to this subspace. We have seen that the dimension of the image of a matrix is equal to the rank of the matrix. So this value is equal to the rank of this matrix AB. And this value, the dimension of the image of A, is equal to the rank of A. And so the inequality holds. And we have finished proving part 2 of exercise 8. Finally, we will show part 3, which looks very similar to part 2, except I have swapped the rank of A with the rank of B. We will in fact use part 2 to answer part 3. And the trick that I will use is to reverse the order of multiplication without changing the rank. And I will use the transpose. Because the rank of a matrix is equal to the rank of its transpose, and the transpose of a product is the product of the transpose in reverse order. Let me write these bigger over here. I will replace this with the rank of the transpose of AB, and I'm allowed to do that because of part A. Next, I will apply part B. I will replace the transpose of AB with B transpose times A transpose. Then part 2 tells me that this rank should be smaller or equal to the rank of the first matrix. And remember, my goal is to show that the rank of AB is smaller or equal to the rank of B, and I'm very close. I can replace the rank of B transpose with the rank of B. I've shown that the rank of AB is smaller or equal to the rank of B. We were able to show this fact, which would be very difficult to show by directly computing the leading ones using the definition of rank, but using the idea of dimension, we were able to do this without much extra work. By combining part 2 and part 3, we have that the rank of the product of two matrices is smaller or equal to the smaller of the rank of one matrix and the rank of the other matrix. This is the end of lecture 14b. Thank you for your attention.